Hello and welcome to the second video of our chemical energy storage charging technology sequence. And in this video we will deal with the generation of hydrogen. And when we first look what are the pros and cons of hydrogen. First of all, hydrogen is the most common element on Earth, so it's highly available. It has a high gravimetric energy density. Its combustion product is just water, so it's environmentally friendly. Its sustainable production is possible by renewable power, by solar thermal and also by bioenergy. And this so-called cold combustion can also provide high efficiencies. And it can be applied cross-sectoral. That means when we once have produced the hydrogen, we can use it in the power sector, in the heating sector, and also in the mobility sector. There are also some disadvantages. So it has a low volumetric energy density, at least compared with other hydrocarbons. The process to generate hydrogen is energy intensive. The water electrolysis has quite a high loss potential, and hydrogen is highly explosive, the oxyhydrogen reaction. And maybe also we can name the high flame velocity, so it's not so easy to apply it in conventional combustion processes. When we look how we can produce hydrogen, we have many different possibilities. But first we have a small video, also a bit of funny video. Taking a well-known example from Praxis, we illustrate the charging technology power to hydrogen with water electrolysis with a fuel cell car. Different to all available cars, this innovative car is equipped with solar cells in order to drive in complete autarky. Ladies and gentlemen, we proudly present the Optimus PEMEL Deluxe Mobile. This car is equipped with the latest high-end solar photovoltaic technology, allowing the complete renewable driving concept. And then the heart of the Optimus PEMEL Deluxe Mobile, the PEM fuel cell. In the electrolyzer, water is split into hydrogen and oxygen. Those gases are stored independently from each other in the two maximum safety tanks. By means of them, the Optimus PEMEL Deluxe Mobile achieves a driving range of incredible several meters. Once charged, the two tanks serve as fuel for the Optimus PEMEL Deluxe Mobile and its fuel cell. With the help of a controlled detonating gas reaction, electricity is generated and the electric motors are supplied with. These motors develop an enormous driving power that you immediately will experience with your own eyes. As soon as sufficient fuel has been generated, the motors are started. It's so incredible, it's so fantastic. When you once have driven this car, you never want to drive a diesel car anymore. So when we look for the charging technologies, how to produce hydrogen, then we see here we have many processes to do so. On the complete left side over there, we have the electrolytic processes. Then more in the center, we have the thermochemical processes, and then more here on the right side, the photolytic processes. And when we start with that, what we have here in this red box with the conventional hydrogen production, we have there on the left side, it's the chlor-alkali electrolysis, and that is a way where we use hydrocarbons, where we use fossil energy to produce chlorine. But then a byproduct is the hydrogen that of course we also can store and then use in the energy sector. And we have in the center the hydrocarbons. There we mainly can gain them again out of fossil fuels by a steam reformation process. But again, it's a fossil product. And then also we can have solid hydrocarbons like coal, that in the gasification process we also can gain hydrogen. So when we sum up that the chlor-alkali electrolysis, there the hydrogen is just only a byproduct. We do that process because we would like to gain chlorine for the chemical industry. But nevertheless, as chlorine is also a storageable product, we can use that in order to support the renewable energy system, as we use then the excess electricity then when it's available to produce the chlorine. When looking for the reformation and gasification process, it's a production of hydrogen mainly by the steam reformation of hydrocarbons that contain a lot of hydrogen like methane and methanol, and the production of hydrogen by gasification allows also to use solid fuels. These conventional production schemes, they have a very big advantage, and that is the low production cost. There we have a kilogram of hydrogen produced for more or less €1. And that is much cheaper than all that what we nowadays try to use using renewable electricity like solar and wind. But of course it is not a solution, because the disadvantage, we use here hydrocarbons as an adduct, and we want to go in a renewable future. And then we also need to say it's only a conversion, because already the adducts are already a storable product. So that is not really what we are thinking of when talking about renewably generated chemical sources that we can use to store renewable power. Coming now to the more interesting processes. More interesting because we are now talking about the climate neutral production of hydrogen with renewable energy sources. And there first we have on the complete left side the water electrolysis processes using all the fuel cell technologies we know. But then we also have from the thermochemical process the high temperature water splitting, where we directly could use solar radiation, highly concentrated solar radiation. And then the third on the right side, the photolytic processes. And let's start with that last example, the photolytic processes. Photolytic production of hydrogen via electromagnetic radiation. And there we distinguish two possibilities. First is the photobiological process that is powered by microorganisms and light to make artificially the photosynthesis process. And then we have the photoelectrochemical process that is powered by special semiconductor devices. Whenever we would make that to become realized, that would close the carbon cycle. That means the combustion product CO2 is then the new energy source that we use to produce new hydrocarbons, new hydrogen as media that we can store. On the other hand, we need to say that these photolytic processes at the moment are still part of basic research, and it's not available, those processes, for nowadays energy transition process. Coming to water splitting with concentrated solar power, that is a way where we also can use renewable power directly to generate hydrogen. And theoretically, we can split water, the H2O, when we have heat at a very high temperature level of more than 3000 degrees Celsius. And as that is quite difficult to produce, or a higher expenditure with lower temperatures, then we try to substitute this single stage process by a two-stage process that works with lower temperature levels. And there it's possible to work then with temperatures between 600 and a bit more than 1000 degrees Celsius. And there we use metals that work as a catalyst. And that is what we see here in this cycle process. And there, first we look to the left part, to the reactor we see there on the left side. coming from the box on top is the metal oxide. For example, it could be the zinc oxide, and then with help of high temperature solar radiation, we split the metal, the zinc, and store then this zinc powder, and the oxygen that we split away from the zinc oxide, that is released to the atmosphere. And then we have the second stage reaction. Then we use the zinc and bring it together with 2 parts of water, that again with the high temperature is then in a gaseous form, and then that reacts to 2 parts of zinc oxide, and then we have the circle closed again. We have the zinc oxide, that was the starting product of our 2-stage cycle, and we have 2 parts of hydrogen, and that was what we have intended. We wanted to gain hydrogen, and this hydrogen we then can store and later use it in the energy sector. And then we come to the water electrolysis, maybe the most famous one, where we can use electricity, maybe surplus, excess electricity from renewable power. And there we have 3 electrolysis processes available. First is the alkaline electrolysis, then it's the proton exchange membrane electrolysis, and the high temperature electrolysis, also called the solid oxide electrolysis. Here we have a high level of integration of renewable energy. It's a climate neutral storage process that we enable. We have maybe problems with storage and transport, not optimally adapted to the current energy system when we stay with hydrogen. Water electrolysis is the core component of chemical energy storage. Of all those processes we call nowadays power to gas, power to liquid. And the power to gas, power to liquid process supplies synthetic hydrocarbons by means of renewable power. So which electrolysis processes do we have? First, we have the alkaline electrolysis, AEL. There we have a cell with alkaline electrolysis. So 2 half cells separated by an ion conducting membrane. And then we have porous electrodes with a very large surface on both sides of the membrane, and that are very close to the membrane. And when we now connect the voltage that is bigger than 1.23 volts, the water is split at the cathode in atomic hydrogen and hydroxide ions OH-. So 2 parts of water in a liquid form with 2 electrons. They then form hydrogen, that is in a gaseous form, and 2 OH- ions. Then the protons, they react to hydrogen molecules, and the OH- ions, they diffuse at the anode and react to water and oxygen. So 2 of those ions, they react to oxygen, again in the gaseous form, plus water plus 2 electrons. And then maybe more meaningful is the PEM electrolysis, that is better suited because it has better dynamic performances, and especially those dynamic performance we require when we want to have the fluctuating wind energy, for example, integrated and used then for a source for production of hydrogen. So the PEM on both sides is firmly connected to the electrodes, and it's solid, a highly porous polymer electrode, and that affects then on the electrodes that the current flow comes to the electrodes, and the transport of water to the anode, as well as the transport of the produced gases away from the cathode. The added water with a voltage UZ is then split in oxygen, a positive charged hydrogen, and electrons. So the water that goes inside the electrolysis in a liquid form, then we produce the oxygen in a gaseous form, 2 ions of hydrogen and 2 electrons. And the H+ protons then diffuse to the cathode side and react with electrons to hydrogen molecules. So 2 hydrogen ions plus 2 electrons, and we have what we want is the hydrogen again in a gaseous form. And then we have the high temperature electrolysis, also called the solid oxide electrolysis. A part of the splitting energy we need to produce the hydrogen here is supplied by the high temperature heat around 850 to 1000 degrees Celsius. That decreases then the required cell voltage to less than 1 volt, and we have high electric efficiencies that result from that. It's the reverse reaction of the solid oxide solid fuel cell, and the half cells are separated by an oxygen ion conductive solid electrolyte, and at the cathode overheated steam is added, which reacts with electrons to hydrogen molecules and oxygen anions. So water plus 2 electrons then is split into hydrogen and oxygen ions, and the oxygen anions diffuse to the anode and oxidize by releasing electrons to oxygen molecules. So the oxygen ions react to oxygen and to electrons. And now we have learned about different ways to produce hydrogen, and we also have learned that there are some advantages but also disadvantages. And now in the next video we look then to the generation of methane and other chemical energy carriers. Thank you very much.